sort of out of the beaten path, if you will. And this was a great announcement yesterday. I know a lot of people saw it, but I felt like we should share this news with everyone. And that Microsoft yesterday at OCP, at the OCP Summit in San Jose, announced their commitment to use ARM server chips. And that's a huge endorsement for ARM and the enterprise server as it moves forward. So I felt like that was great news. I wanted to make sure everybody was aware of it. And we're really fortunate to have, I think everybody knows that Facebook is actually a member of Linaro, and we're really fortunate to have Max Wang with us here this morning, and he's going to talk to us about HHVM. Matt, please join me in welcoming Max.
Morning, everybody. Let me get this set up. In the meantime, thank you so much, Joe, for the introduction. Thank you all for having me here today. Soon. All right. So like Joe said, my name is Max, and I'll be here talking today about HHVM on AArch64. So this talk's basically going to boil down to answering 4 high-level questions. The first is pretty straightforward. What is HHVM? It's very straightforward. Is it an animal? Is it a vegetable? Or is it a mineral? It's got to be one of those 3 things. Hopefully, we'll find out which of those 3 things it is. We'll talk about what HHVM is used for. We'll talk about who uses it, and we'll dig into the architecture a little bit. Second question, I wanted this to be what is AArch64, but I felt like maybe a few people in the room might already know that, so I switched it up. We're going to talk about how we actually got running on AArch64, what were some of the challenges in getting us ported over. And the most important part of this section, and really the most important part of my whole talk, I think, is I want to highlight the engineers who actually made this port possible. So that's part of the how is the who. I really want to sing the praise of open source. Without open source, I think that this port probably wouldn't exist. I certainly wouldn't get to fly out to Budapest, make a fun talk. And I think that without open source, without the sort of developer community, we wouldn't be driving the hardware landscape forward like we are. So, the third question is mostly for me. Is the demo going to work? There is a demo. This is supposed to be a joke, but actually yesterday I managed to brick my, my host. So hopefully we'll actually see the demo functioning, and if not, we'll figure something else out. The last question I'm sure I can answer, where do we go from here now that HHVM has been ported to AArch64? What work is left to do, and how are we going to do that work? And there is plenty of work to get done after this. So jump right into it. What is HHVM? So in a sentence, HHVM is a just-in-time compiler for PHP and Hack. And we'll sort of parse this sentence a little bit. PHP is something I'm sure that many of you have heard of. It's a very popular web programming language. It's also a dynamic language in the vein of something like Python or Ruby. PHP is a little special. It's particularly known for having a few, we'll say, quirks. Divide by 0 is false. Got a little PHP caught in my throat. All right. But we'll look at a little bit of PHP's sort of odd behaviors here. So as you can see, strings that look like integers in PHP behave like integers, except for when they don't behave like integers. And when we use strings in contexts that expect arrays, they behave like arrays of characters, except, of course, when they behave nothing like arrays of characters. WAT. So this is a famous slide from a famous talk, but this is actually not that talk. So we're just going to move on, because what I really want to point out about PHP is that there are a lot of benefits to using PHP, even though it might sort of have some bad rap. And one of the major benefits is something it shares with other dynamic languages like Python and Ruby, which is that there's a very fast development cycle for developing PHP. If you're a web programmer, you write your code, you hit your web server, and all of the bugs you've added to your code are now there, and you can sort of debug them, and product engineers love doing that, so we want to make sure they can do that as fast as possible. One thing that PHP is very good about that is actually not shared with most other dynamic languages is that PHP was designed pretty much specifically for web programming. So when you send requests to PHP, each request is completely isolated. There's no memory shared between them at all. Every request starts off with a clean slate, and that's something that's really useful for web developers. It's really easy to reason about, and that's actually a major benefit of PHP. But as I said, HHVM is a just-in-time compiler, not just for PHP, but also Hack. So what is Hack? Well, Hack is a language that we developed at Facebook. We built it on top of PHP, and it takes those really nice benefits of using PHP and sort of tries to augment them with new features to try to mitigate some of the weird problems that PHP has sort of developed. So some of these features include you can do strict typing in Hack, but you don't have to do strict typing in Hack. You can type your code gradually if you wish. We also have async execution, which is a feature we borrowed from C#. And we have better collection types like dict instead of PHP's very generic array data structure, which is a vector, a set, and a map. It's very odd. But we've sort of added new features. And there's plenty more features beyond this, so that I won't sort of dive into too much here. So what else is HHVM for? Well, Facebook's business logic is written largely in Hack, and so obviously HHVM is going to be serving Facebook's web production traffic. So whether you hit the desktop site, the mobile app, Facebook's APIs, all of the stuff, a lot of this stuff is going to go through HHVM. So what else does that mean for HHVM? Well, it means we have to be fast. If you're running the biggest social network in the world, you need to run quickly, you need to run efficiently. And since we've switched to HHVM compared to how we were performing before, we've gotten orders of magnitude of performance improvement. Of course, it's been probably 5 years at least since Facebook could actually run on stock PHP. So don't take our word for it. As I've sort of alluded to, Facebook is not the only user of HHVM because HHVM is a fully open source product. You can find us right on GitHub. All of our development is sort of done in the open. All of our code base is out in the open. And in fact, HHVM is now used by 3 of the Alexa top 5, or at least the Alexa top 5 from whenever I took this screenshot of the Alexa homepage. So Facebook obviously uses HHVM, but so does Baidu, the Chinese search giant, and Wikipedia, the free encyclopedia. Baidu has most products migrated to HHVM, and when Wikipedia switched from PHP 5 to HHVM, they got a nearly 6x improvement in peak CPU utilization, which is pretty substantial. That's not it. There's other smaller services like Box and Slack and Etsy. These guys are using HHVM, and HHVM also supports many common PHP frameworks, WordPress and Drupal, and also developer frameworks like Magento and Symfony. These guys can all use HHVM. So going back to this sentence, in a sentence, HHVM is a fast, open source, just-in-time compiler for PHP and Hack. So finally, it's time to talk about that just-in-time compiler part, and that's the most interesting part. Let's talk about an ahead-of-time compiler. Let's start with that. So HHVM is not actually the first PHP runtime that Facebook developed. That honor goes to the hip-hop for PHP compiler. This is sort of how things started. We weren't satisfied with the performance of PHP, so what we did, we did what anyone would do, and we decided to transpile our PHP to optimize C++ code. Then we simply ran GCC on that code, produced a binary, and that binary was facebook.com, the web service, the whole thing. But there are sort of some obvious issues with doing ahead-of-time compilation, which is why we switched to a JIT, and I want to explain this to motivate why we are doing just-in-time compilation. So obviously, ahead-of-time compilation is this sort of slow ahead-of-time compilation step. It's exactly what it says in the box. This sort of it flies directly in the face of one of those benefits I said that PHP had, which is this fast developer cycle, right? If your developers need to spend 20-some-odd minutes compiling their website, because Facebook is a large website, first of all, they're going to come after you, the compiler engineer. They're going to murder you in your sleep. So you won't really have any problems after that. But after that, they're going to complain a bunch and be really sad, and development's going to be a nightmare. So we actually had to create a separate essentially a separate runtime for development called HPHPI, the hip-hop interpreter. This created a new, fresh problem, which was that suddenly we have to maintain essentially 2 separate systems, one for testing, one for production, and this is really not ideal. There are other issues as well. One of them is that the binary size of the compiled facebook.com binary actually became so large that it became troublesome for deployment. So that was another issue. And the third issue is one that's easily overlooked, but also very significant, which is that PHP is a dynamic language. If you're doing only static analysis and static type analysis on the language, you're sort of going to miss out on a lot of opportunities. Let's say you have a function that takes either a user ID or an array of user IDs, and don't ask me where I got that idea from. Suppose you have such a function. Doing only static type analysis is only going to get you so far. You're not going to be able to optimize all that you want to. So that's why having just-in-time compiler is useful, and I'll sort of give a brief tour of the pipeline that we're using today to do just-in-time compilation. So we start nowadays, dynamically at runtime. We'll take PHP and compile it down to what we call hip-hop bytecode. This is a very high-level intermediate representation of PHP. I'll give you a small taste, or some might say a bite of this. So suppose you have some code like this. you're setting some variable $elem, and then you check if it's 0 or it's greater than 0, and you do something. So we have the bytecode over there. It's pretty straightforward. It does look a lot like PHP. We set local with ID 4. So this bytecode starts, there's something on the stack. We set that value, we set that to assign that to local 4. Then we pop the value off the stack. We put an integer on the stack. We put another local on the stack. We do a greater than comparison. We jump somewhere. Sort of very much like the semantics of PHP. There's an obvious translation from this PHP code. This is a stack-based bytecode, and it is pretty far away from the metal. It's pretty far away from assembly, and there's sort of clearly PHP semantics involved. For example, the greater than bytecode will compare any two PHP values according to the PHP semantics, which are pretty convoluted and has a number of cycles. And I promise not get into that too much. So bytecode wasn't enough for us. We wanted more performance. We wanted more optimization. So we added another layer. And this layer is called the HHIR, the HHVM intermediate representation. HHIR is a static single assignment representation. It's a lot closer to the metal. It's a lot closer to the actual assembly we're going to output eventually. But you can still see the PHP language semantics present. This isn't a great example. The HHIR on the right is mostly loads and stores from locals and stack slots, but that sort of gives you a sense. Locals and stack slots are obviously going to compile down to direct memory addresses, but there's still sort of the semantics of which local are we talking about, which stack slot are we talking about. Those semantics are all present, and other HHIR opcodes will sort of encapsulate the semantics of PHP calls, the weird semantics of PHP division, which can sometimes return false, et cetera. And just to be complete, even though I'm not going to talk too much about this part of the pipeline, we also do an optional ahead-of-time compilation step still. This lets us do whole program static type analysis, and that does give us something that we can't do dynamically. They're going to be type assertions that we sort of can't obtain by profiling and running code and sort of seeing how it actually works. So this gives us the best of both worlds. Again, that's not where I want to focus too much. I want to focus on this part of the pipeline because this is where the magic happens. This is where you get the benefits, you reap the benefits of being a just-in-time compiler specifically. So let's look at an example. This example is a little busy. It's a little complicated, but it's try to explain it a little bit. So we have this function on the left, add positive. It's essentially iterating through a PHP array, which again is sort of this generic data structure that maps arbitrary keys to values. And it's adding all of the elements that are positive, right? So on the right is the HHBC translation, the bytecode translation of that PHP code. And in the blue boxes are the type guards, right? So again, we are a JIT, so we're able to do dynamic type specialization. So as we see code, we can observe the live types, and then we can specialize the code according to those live types. So you'll see that the first sort of block-like piece of code that we're translating is this loop comparison, $i less than $n. So this we can specialize to actually just a comparison between two ints. Again, in general, the bytecode LT less than has to sort of encapsulate all of the interesting PHP semantics of the less than operator. But here we don't have to do that. We observe that these types are always integers because one of them is the integer iterator and one of them is the size of the array. So this makes our lives pretty simple. We end up compiling that first block up at the top right into just a regular integer comparison. Very nice, and then the rest of this is essentially similar. We sort of observe all the different live types. If we end up failing these guards, we'll side exit, we'll run the interpreter, or we'll do another translation. And as you can see, there can be some fan out to this strategy. So in this particular case, let's say we get arrays that are full of either ints or doubles, or maybe a mix of integers and doubles. We will have to specialize on sort of every combination of integers and doubles between the aggregator and these elements of the array. So that is sort of one downside here. But obviously, we can do better than that, and we do try to do better than this. So we can do profile-guided optimizations. So when we first do these translations, we'll add profile encounters to the code. And as we hit these profile encounters, we'll discover which paths are actually hot, which of these are essentially sub-basic blocks. We call them tracelets. We sort of need to make a new one every time we need more type information. But we'll see which of these are actually being hit. So let's say we only hit the ones that have been highlighted. Then what we can do is we can take these tracelets, the hot tracelets, and we can glue them together. We can sort of make a straight line region that sort of lets us optimize this code even more. So there are a lot of benefits to making this read in straight line. One of them is that we can eliminate some of these redundant guards. As you can see, we don't need to check that $I is integer multiple times. And we don't need to check that $lm is a double anymore because it was, $lm is just exactly what was on the stack before, and we've already checked the stack slot. That's one reason, rather. This is also better for code locality. By making this a straight line region, we don't have to have all these sort of sub-basic blocks floating around, jumping to one another. We just have this straight line pass, and it's a lot better code. Well, that's all we do. We do plenty of traditional compiler optimizations as well. We do most of these at the HHIR level, and the reason for that is because the HHIR level still has PHP semantics baked into it. And sometimes we really need those PHP semantics in order to actually do our optimizations. The example I've chosen here is ref count optimizations in PHP. So PHP is a reference counted language. The types, all of the non-scalar types are reference counted, and the effects of reference counting are observable at the language level in PHP, which is not the case in many other languages. PHP has precise object destruction semantics, so as soon as objects go out of scope, you have to run their destructors. Arrays are also copy on write, and copy on write, surprisingly, also has visible user effects. So as you can see, reference counting can be pretty expensive. There's going to be a lot of reference counting that we do when we generate PHP code. But we can sort of get rid of a lot of it. We can knock out most of those reference counts by doing analysis to prove that some of those ref counting operations are not needed, to prove that some of the sort of increfs and decrefs and support for the reference counting of the types are never observed. But to do that, we do need knowledge of PHP semantics. We need to make sure that we're not going to re-enter the VM. We're not going to throw in some way that's surprising. We're not going to sort of execute all these paths that are going to rely on the reference count being actually visible and written to. So that's why we need to do this at the HHIR level. But once we do, we get to condense the code substantially. It gets a lot tighter. It gets a lot better. And of course, that's not the only optimization pass we have. There's plenty more where that came from. We do function inlining. We do load and store elimination. Those in particular both need to rely on very heavily on semantics of PHP. Load store elimination in HHIR level really benefits from having sort of a semantic-laden alias analysis of memory effects. We do constant propagation, dead code elimination, plenty of like local people optimizations. We do plenty of the classic compiler stuff. So that's sort of our tour of the basic compiler pipeline. I'll give you a general sense of what our architecture looks like and some of the specific optimizations we've added. So let's talk now about how we actually got running on AArch64. So go back to this picture. This is exactly what HHVM looked like when we started thinking about ARM back a few years ago. Exactly like this, 4 boxes, 3 straight arrows, 2 loopy arrows, 1 happy compiler. Our first attempt, or our first foray into the ARM space was something that we handled mostly internally. So since we handled internally, we hacked it up in a sort of classic Facebook fashion. Rather than attempting to actually target the hardware, we used the VXL ARM assembler and just assembled, we generated ARM code on our x64 machines, and then we used the VXL simulator to simulate running that ARM code on our machines. So there are some obvious downsides to this. First of all, we do get to test sort of lowering HHIR to ARM, and we get to test that JITted code. But we don't get to test the code that's at the boundaries, the boundary crossings between the JIT and native runtime helpers. And obviously, those native runtime helpers are also still running on x64. They were compiled by GCC. They're still running x64 code. But one would think that we are getting some benefits. We are getting to see how our JITted code will actually run on ARM. And that was true for a while. But it turned out that over time, this became something of a huge maintenance hassle. We have over 600 HHIR opcodes, and the number grows with time. The reason for that is because HHIR is essentially a purely internal API. There's no external consumers or producers of HHIR. It's just something that we use as our middle end. And whenever we go into performance lockdowns, we'll create new HHIR opcodes, or we'll change the APIs of existing instructions. And every time we do this, it sort of ends up being a lot of churn if we need to sort of have all this copy pasta between the x64 version of that instruction and the AArch64 version. We're essentially, a lot of these codes, again, a lot of these HHIR instructions are really close to the metal, so we're essentially just writing two exact instruction sequences that are functionally the same in two slightly different assembly languages, which is really not ideal. And it turns out that even though we had something like, we had continuous integration testing to sort of keep us honest and make sure that we weren't breaking our ARM port, one way we could easily sidestep this is just by punting to the interpreter for all the ARM opcodes we didn't feel like implementing. We were trying to rush and get performance numbers out the door. And that is what ended up happening. So sort of our good faith effort to actually test things running on ARM sort of ended up falling apart a little bit. So how do we solve this problem? The solution is pretty obvious. You just add more abstraction layers. More abstraction layers fix everything. That's sort of the answer to all problems in life. We added a layer called VASM. And VASM is a very low-level intermediate representation. It stands for virtual assembly. And as you can see from the code on the right, it pretty much just looks like x64, but with a bunch of other letters thrown in. That just compiles to a bunch of loads and stores to various memory operands that are sort of given by virtual registers. And this sort of makes sense because one of our explicit goals with VASM was to make it as easy as possible to lower to non-x64 targets while making it essentially zero burden for lowering to x64. And you'll see if you look at this IR that it's very similar to WebKit's, if you're familiar with the WebKit JavaScript JIT. It's very similar to WebKit's new bare bones backend. It's sort of a spiritual sibling of it, even though these weren't developed together, of course. So we're about to add ARM to this picture. But first, I want to sort of address what appears to be an elephant in the room. This is a question I've already been asked twice just in the last 2 days that I've been at this conference, which is, why don't you guys use LLVM? Have you heard of LLVM? I was like, it's great, LLVM's great. You know, like, have you considered it? Have you heard of this technology? The answer is yes. We have heard of LLVM. And initially, the reason we didn't use LLVM is because, first of all, we wanted to get the project ramped up quickly, so it was easier to sort of handle a lot of the stuff ourselves, especially because we were particularly concerned about JIT speed and code size. We wanted to make sure that we would be able to control those elements very tightly. As things progressed and as HHVM sort of started to mature, we realized these things weren't as problematic, so we did actually experiment with an ARM backend, or sorry, with an LLVM backend. But unfortunately, it just wasn't particularly fruitful. So we think that one of the reasons that this was the case is because most of our optimizations, most of our particularly good optimizations, ref count ops is one, load store elimination is another. These things all rely on our knowledge of PHP semantics at the IR level. This is something that LLVM just can't take advantage of, and it's something that's been particularly fruitful for us. LLVM seems to be good at optimizing sort of static C-like code, which is not at all what PHP looks like. And we sort of we felt sort of justified in this decision. We felt we were like sort of backed in this decision because WebKit did essentially the same thing. So the bare bones backend actually succeeded their previous backend, which was LLVM based, and they sort of had the same experience. They found the LLVM JIT was sort of cumbersome. It was pretty heavyweight, and it didn't give them as much performance as they would like. And they found that having a faster, sleeker, very simple, low-level representation was just as good for them. So one thing that the LLVM experiment that we took on did give us is it actually let us stress test VASM. Like I said, the sort of primary goal when we developed VASM was that it was easy to lower it to x64. But that meant we didn't really test as much lowering it to any other targets, and when we did the LLVM backend, we actually got a lot of practice doing this. We had to make sure we had sort of, with safety for our registers, we had to make sure we handled all the interesting ABIs that HHVM has well. We had to make sure that we could smash instructions correctly. That's sort of how the JIT operates, is you have some call, and then you smash over the call that originally calls into the compiler and then eventually calls into your translated code. We had to make a lot of changes to VASM, and that's sort of what ultimately enabled our ARM port. And just for good measure, we also port to PowerPC now, so HHVM targets ARM, PPC, and x64. Okay. So this, as I was saying at the beginning, this is what I think is the most important slide in the talk. This is really the most important part, because none of this port would have happened without the ARM community. In particular, these are some of the developers that have made serious contributions to our port. These are these folks with GitHub commits. There's other people as well who have sort of contributed knowledge and time into the port. These guys were willing to engage at an early stage and sort of get their hands dirty to push the hardware forward. These are engineers from Cavium, Qualcomm, APM, Theobroma Systems. They've been working on this port since late 2015, so it's been about a year and a half now, and they've gotten a lot done, and they've really gotten their hands dirty. They've really sort of dug in. So huge thanks to them. So what did they actually do to get the ARM backend working? Well, they had to do sort of the bare basics. They had to lower VASM to ARM, to AArch64. They had to sort of handle all of the alignment issues, the synchronization issues, the cache line tearing issues around code smashing for when we need to sort of smash the targets of calls and jumps. They had to navigate all of HHVM's complex APIs, or ABIs rather. They had to deal with VM reentry. They had to deal with callee save registers. They had to deal with some of the unique calling conventions that we have for certain special kinds of calls. Obviously, this is all very well documented, obviously. So there's no struggle at all, for sure. And plus, they had to do all the debugging around sort of platform configuration, dependencies, all the sort of classic problems you have porting any system to ARM. And they handled this with grace. And as a bonus, they also set up continuous integration testing for ARM. So now we are actually sort of held accountable for breaking changes that we might make. And there's no way for us to cheat now. But that's not all. They didn't just sort of get the baseline functionality. They also implemented some optimizations of their own. So one of the major ones is strength reduction on flag setting instructions. As you may know, on x64, arithmetic and bitwise operators, bitwise instructions, always set the flags register. On ARM, this is not the case. You can optionally set the flags registers or not. This is something that we had to actually add an optimization pass for because, again, VASM was sort of targeted towards x64 from its start. Another one is lifting 64-bit immediates. So on ARM v8, all the instructions are still 32 bits in length, but we still have 64-bit immediates that we have to deal with. It's pretty expensive to build up these immediates, so we can sort of do some content subexpression elimination and actually sort of pull some of these into registers and persist them across small units of code. Another one is that we can avoid some indirect branches. When we first generate VASM, we have to be very conservative because we don't know where these branches are going to go. We don't know how far away they're going to be. Especially when we emit instruction sequences where the branch target or the call target might need to be smashed over later. We need to be very careful about how we actually lay that out. But later on, we can sort of elide some of this. We can rewrite some of these instructions to be direct calls, direct jumps, avoid some of that pessimization. All right, so now I want to try to actually prove that this port is functional by doing a demo. So it'll be a terminal demo. I'm sure we all like terminal demos. Let me see if I can drag this terminal window into, does anyone know which direction this is? Oh, there we go. We did it. All right, so, and I can't see. So this is an ARM host that I'm working on, and it is not responding. Oh, there we go. OK, so here we have HHVM running under Siege, which is basically a tool that sends a bunch of requests to a server. And this HHVM instance is running MediaWiki. It's running a MediaWiki benchmarking suite. And to prove that we're actually running on an ARM machine, there we go. It says AArch64 3 times, so you know it's true. Oh, this command is taking a long time. All right, so let's send a request to this HHVM instance, and we'll see how long this takes. So we're looking up the Barack Obama page. The reason for this is not just because I felt like looking up the Barack Obama page. It's because that's actually the page that Wikimedia used for testing. And there we go. We get a bunch of nonsense HTML, and I'm not going to render this because I'm a systems developer and I have no idea how. So this is all you get. But as you can see, this is our machine. We have HHVM running. There you go. So let us return to this. OK, great. So the demo worked. That's great. I'm very happy about that. So let's talk quickly about where we go from here. Because like I said, there is plenty of work still to be done. So one of the major areas of work is code size and layout. Cache is king. This is very true for HHVM. We've always been particularly cache bound. And instruction sequences, as you know, tend to be larger on AArch64 than on x64 for essentially the same operations. So we're even more sensitive to code size and layout on ARM than we are on x64. So there's a bunch of strategies we've considered to sort of mitigate this problem that some of these developers have already started to explore. One of them is using huge pages. On x64, we use 2 meg or 1 gig pages for both the text section and for JIT code. And that's something we're not currently doing on ARM, but we would like to. We can also use relocation, as I alluded to earlier, to reduce the size of branches, especially branches for smashable code sequences. We need them to be particularly laid out in a particular way before we've smashed the targets. But after we've smashed the targets, we never smash them again, so we can streamline those branches, we can shrink them, make the targets direct. We can try interleaving hot and cold JIT code to avoid indirect jumps, because on ARM, I believe, direct jumps can only support 26-bit offsets, and then conditional jumps only support 19-bit offsets. So we can sort of change the layer of our JIT code to accommodate that. Then we can do other kinds of tuning. We can tune our linker script that links our native functions in order of hotness. We can tune that to ARM workloads. And we just generally tighten our code output for the JIT for ARM specifically. And besides that, there's sort of some more general work we can do. We can profile open source workloads on ARM using perf. That's something we haven't gotten to yet, using the OSS performance tool, which is the tool you just saw in the demo. We can actually, in the long run, at some point in the future, we can actually make some measurements, maybe measure against x64, and see how our performance actually compares to that. So, if any of you are interested in getting involved, or even just following along with this work, feel free to contribute. Feel free to take a look at HHVM. Our website is hhvm.com. You can also find us on GitHub at Facebook/HHVM. You can also join us on IRC. We're very traditional. You can come onto #HPHP dev on Freenode. We have a mailing list for development of the ARM port. And if you forget all of these details, then you can always just email me at mwang@fb.com, and I can provide them to you, and I can try to help you get started if you're interested in joining. So that's all I've got. Thank you so much.
Thank you so So we do have a couple minutes.